So in this video we're going to talk about redox reactions. That's the general topic. Within redox reactions we're going to look at oxidation states and then relate it to mainly ionic compounds, which we've learned a lot about so far. The big takeaway from this video and this subject is understanding how reactions happen and then why reactions happen. And the good news is you already know a lot of the information, because most of the reactions that we'll look at involve electrons, and a lot of it involves losing or gaining electrons, which is the definition of ionic bonding. So we're going to start by looking at ionic compounds, and then we're going to look at a really easy, familiar reaction, and then relate it to all this information. So the reaction that we start with is sodium reacting with chlorine, and that forms sodium chloride, NaCl. We can't do this reaction in class, unfortunately. Sodium is really dangerous, and so is chlorine gas, but generally the reaction happens because you can take sodium, heat it up in the presence of chlorine gas, and it forms sodium chloride. Sodium reacts, or it is reactive, because it has one electron in its valence shell, which is looking to lose. Remember that metals generally lose electrons to form cations, positive ions. Non-metals generally gain electrons to form anions, and chlorine has 7 electrons in its valence shell, so it wants to gain one more. So needs to lose one, needs to gain one, match made in heaven. If we looked at the ions in this substance, we'd have Na plus attracted to Cl minus, sodium lost an electron and became a plus, chlorine gained an electron and became minus. So plus and minus, electrostatic attraction. But that's the basic idea, and we've learned a lot about ionic bonding and why it happens and how it happens and so on. So we're going into more detail now. So let's just look at sodium on its own. I'm just going to fix that. So you know that sodium is in group 1 on the periodic table, needs to lose that electron. The next shell down is full with electrons, so losing an electron is more stable, makes sodium more stable. So the way that we represent that is like this. And this is called an electron half reaction, which we'll learn a lot about, but the name of it is an electron half reaction. So what we're saying here is that you take an atom of sodium and it forms an ion, in this case a cation of sodium, and it does that by losing an electron. Chlorine, on the other hand, gains an electron to form Cl minus. So what we're saying here is that you take an atom of chlorine and you add an electron to it and it becomes a chloride ion. So electron half reactions. If we combine these two and just eliminated the electrons because they'd be on both, they kind of cancel each other out, we'd have Na plus Cl gives NaCl. Well, actually no. So we have the ions. So we've gone from atoms to ions. And so if you want to think about this in an easier way, perhaps, you can think of this arrow as an equal sign. So what we're saying is, if you take an atom of sodium and you take an electron away from it, it equals a sodium ion and an electron. So if you went back this way and added these two things together, you'd get an atom of sodium. Same down here. You've got an ion of chlorine over here, and if you went back this way to split it back up, you'd have an atom of chlorine and an electron. And then overall, you've got atom equals ion plus ion. And all that's changed is that sodium gave up one electron to the chlorine, and that's how we represent it. So this would be the combination of the two half reactions. And we'll get a lot of practice in this, and so perhaps not worry about that too much right now. So let's relate it to the general topic, which is redox reactions and then oxidation states. So oxidation has different definitions, and the opposite of these represents reduction, or the definitions of reduction. So if something gains oxygen, we say it's been oxidized, and the name oxidation kind of implies oxygen in some way, but not in every case because there's no oxygen being involved in this reaction down here, although there has been oxidation. So if something loses an electron, it is oxidized, and so the sodium down here would be oxidized because it lost an electron. And if something loses hydrogen, it's also oxidized. It doesn't really apply in this case, but this second definition does. So the sodium has been oxidized. So the opposite of oxidation is reduction. Oh, just one last thing about oxidation. If you take a piece of fruit or a potato and slice it, or an apple perhaps, and you slice it, eventually it turns brown. And it's because there's a chemical being oxidized. So it's gaining oxygen from the air. So it's not really doing the losing hydrogen part, it's just gaining oxygen from the atmosphere. And there's a chemical reaction and it's changing that chemical into that brown stuff that forms a coating on the outside of the apple. Also, rusting is oxidation. If you take a piece of iron, and leave it out, it'll eventually rust from a little moisture in the atmosphere as well, but mainly oxygen. So the metal plus oxygen gives you the rust. So the opposite of oxidation is reduction. So if something loses oxygen, it's reduced. Doesn't apply down here. Gaining an electron, though, does apply because the chlorine gained an electron. And then if something gains hydrogen, then it's also reduced. So only one of these definitions applies in this example, and that's this is being oxidized, this is being reduced. So because both are happening in the same reaction, we call it a redox reaction. So kind of a combination of reduction and oxygen. And many, many reactions are redox reactions. It's actually easier to come up with more redox reactions than just oxidation reactions or just reduction reactions. So very, very common type of reaction. But what we're really looking at in redox reactions is, well, what's happening to the electrons? And which one's gaining, which one's losing? This is a very straightforward example, but the idea behind it is the same. So if something oxidizes or causes oxidation, then we call it an oxidizing agent. And if something reduces another substance, then we say it's a reducing agent. So hydrogen peroxide that you get at the grocery store, people use it as mouthwash for cleaning, multiple different uses. Like if you cook yourself, you can use hydrogen peroxide to sterilize it. So it's an oxidizing agent. And it does one of these things. Not every single one, but one or two of these things. Reducing agents do one or two of these things. Okay, so let's look at another example of a redox reaction and then kind of apply some more definitions. So a reaction that we have looked at in class is taking magnesium and burning it in the presence of oxygen. Loads of oxygen in the atmosphere, so there's no shortage. So in this reaction, you actually start with a piece of magnesium metal, which is right there. So if you burn it, you actually form a new substance. So don't look right at the burning stuff because you'll hurt your eyes, but you're getting a reaction, and in this case it's a redox reaction. Difficult to see without moving the camera, but whereas before we had a piece of metal, we've now got this white powder which is magnesium oxide. So we took the metal, burned it in oxygen from the atmosphere, and it formed this new substance. And it's an ionic reaction and it's a redox reaction, and we can apply some definitions here. So what we did was take magnesium, react it with oxygen, and we got MgNO. So all I've done here really is just take the symbols. I've not looked at the charges that these elements have. So this is definitely going to take me a bit more time to examine this and see if it's actually correct, because I need to look at the number of electrons that magnesium will lose, oxygen will gain, and then I need to make sure that this is balanced. So whether the formula is actually correct. So let's do that. So magnesium. If we looked at that individually, magnesium is in group 2 on the periodic table, so loses 2 electrons because it's a metal. So then we can write that this way, loses 2 electrons. And you can think of this 2 as like a coefficient, like 2x, if you're in algebra. So it becomes a 2 plus ion because it loses 2 electrons. Okay. So then oxygen is in group 6 on the periodic table, so has 6 valence shell electrons, so probably needs to gain 2 electrons. So we represent it that way. So an atom of oxygen from the atmosphere gains 2 electrons, becomes an oxide ion. Come on. So we actually form magnesium oxide. So as it turns out, these charges balance each other because you've got a 2 plus and a 2 minus. So this formula would actually be correct. There's a little bit more to say with this formula because oxygen doesn't exist as a single atom in the atmosphere. It actually exists as O2. So I need to show that because it's actually a pair of atoms, not a single atom. And so the idea of a reaction like this is you need to balance whatever's on the left with whatever's on the right. So here I've got 2 oxygens, but I've only got 1 over here. So what I actually do is put a 2 in front of the whole thing. So that makes the oxygens balance because I've got 2, and then 2 times 1 makes 2. So then the only thing that I have to do next is balance the magnesiums because I've got 2 on that side. So that creates a little complexity down here because I've actually got to balance these things out as well. So this would actually be 2 magnesiums here, and balance here. I'll multiply this by 2. So that would actually be 4 electrons. So if it's getting a little complicated already, if you just think about 1 magnesium giving up 2 electrons, and if you have 2 magnesiums, then they'll give up 2 times 2, which is 4. Yes, it is. And if you've got 2 magnesium atoms, then you'll generate 2 magnesium ions. So each magnesium gives up 2 electrons. So 1 gives up 2, 2 gives up 4, 3 gives up 6, and so on. And so then I've got to balance this thing down here. I need 2 oxygens. So if 1 oxygen gains 2 electrons, then that means that 2 oxygen atoms will gain 4 electrons. So I need a 2 right here. Okay. So that got a little complicated, unfortunately, but the idea is that you've got to have something that's losing electrons, something that's gaining electrons in an ionic reaction. So the magnesium loses electrons, oxygen gains electrons because it's a non-metal. So obviously you don't just have 1 atom in every single case. Life doesn't work out that way. So it does get a little bit more complicated, just a little bit. So this again is a redox reaction. So the magnesium is gaining oxygen, so that falls in this definition of oxidation. It also loses electrons, so it falls in that definition as well. So the only one it doesn't apply, the only rule it doesn't apply is losing hydrogen. And then the oxygen doesn't lose oxygen, but it does gain electrons, and it doesn't gain hydrogen. So this is by definition a redox reaction. So let's look at oxidation states, because it's a really important time to kind of apply the redox part to oxidation states. So oxidation states, I'll give you definitions and you'll get notes that kind of explain this in much more detail. But the idea of oxidation states is that in theory, if you had an ionic substance, what charge would each substance have? Right? So let's say we've got magnesium oxide. So you have a substance. If this was ionic, and in this case it is, but if this was ionic, what charge would each substance have? And so there are there's a long list of rules for oxidation states, which I'm not going to go through in this video, but I'm going to be applying some of them. And so definitely worthwhile going back to the rules, and as you practice, kind of coming back to the video as well, and making sure everything's clear. But anyway, group 2 metals become 2 plus ions, and in this case we'd say that the oxidation state of magnesium is plus 2. So one of the first rules of oxidation states is that the oxidation state of something equals its charge, if it's a single ion. So magnesium on its own is a single ion, it loses 2 electrons, so the oxidation state of magnesium equals plus 2. Oxidation states can be positive and negative, whole numbers, they can also be fractions too, which we'll get to much later, but there are a few examples. And so if this is the correct formula, and it is because these two balance out, oxygen has to be minus 2. And in most cases, oxygen has an oxidation state of minus 2. Sometimes it can be minus 1, but if it's bonded to a metal, it's usually minus 2. So, oxidation states, just so far, they apply to a compound, like a mixture of different atoms, and you're really looking at, in theory, if it was ionic, what charge would each one have? And so magnesium here would be plus 2 because it's got a charge of plus 2. Oxygen would be minus 2 because it's got a charge of minus 2. Regular old magnesium, if it's an element, is 0. An oxygen here would be 0. Any element always has an oxidation state of 0, always. Group 1 metals, group 2 metals are plus 1, an oxidation state of plus 1, and then plus 2. Pretty much always. Oxygen is sometimes minus 1, unfortunately, but almost 99% of the time it's minus 2. So let's look at another example. So in H2O, we have a problem because it's not ionic, right? It's covalent. If we looked at it, drew it out, we could look at the electronegativity values of this covalent molecule, and then we'd know that it's got a delta negative end and a delta positive end. So it's a polar molecule. So the rule of a covalent substance like this, if you look at the electronegativity values, or if you just know that oxygen is generally higher than hydrogen, then that would have a negative oxidation state, and this would be positive. And so then you can look at the number of valence shell electrons, and that tells you a lot. So oxygen has 6 valence shell electrons, needs to gain 2. Hydrogen has 1 each, so it needs to get 1 each as well. So the oxygen is going to pull the electrons more this way. So that's going to have more of a negative charge, and because it has 6 valence shell electrons, its oxidation state is going to be negative 2. And then hydrogen is going to be plus 1. So, just to recap oxidation states so far, we're looking at very simple examples, and we will get a little bit more complicated later on, but for right now, an element always has an oxidation state of 0, always. Group 1 metals, sodium, potassium, lithium, all have an oxidation state of plus 1 when they're bonded to something. If something's in group 6 like oxygen, it's very often minus 2 because it gains 2 electrons and has a charge of minus 2 when it's bonded to something. Hydrogen is usually a plus 1, but not always. But usually a plus 1. And if a substance is covalent, you can look at the more electronegative element to see which way are the electrons being pulled. That tells you that, well, probably in this case oxygen would be more negative, and then these would be more positive. Oxygen has 2 electrons as a charge of minus 2. No wait, it doesn't have a charge of minus 2. It's wants to pull these 2 electrons completely toward itself, so in theory, if this was ionic, that would be minus 2, and these would both be plus 1. Alright, so the big idea of oxidation states and redox, we're really looking at why ionic compounds are formed, and in some ways covalent as well, but mainly focusing on ionic compounds, how these reactions happen, why they happen. It's all to do with electrons being lost or gained, and looking at different types of reactions, like an oxidation reaction, which would be one of these, or a combination of these, Reduction reaction will be a combination of these. Usually though, it's a combination of both, right? If something loses an electron, that means, well, probably something's going to gain, right? So that'll be the most common. And so if a combination of these two things happen in the same reaction, like in this one and in most others, it'd be called a redox reaction. So the idea of oxidation state, it's easier for you to look at the long list of rules and start practicing that way. But just to recap, saying it again, elements are zero. If you've got something bonded to something else, then you need to look at, if it's metal and non-metal, well then the charge will tell you. But if you've got something like H2O, then it's probably going to be looking at the more electronegative elements and looking at the valence shell electrons, and then in theory, what charge would it have? So in the next video I'll talk more about polyatomic ions and less straightforward examples and how we work out oxidation states of more complicated polyatomic ions.